This is part 9 of the series Three-Dimensional Solids, and I'm going to start this video with a discussion of spheres. First, I want to give a definition of a sphere. If you remember the definition of a circle, the circle was the set of all points in a plane equidistant from one point called a center. A sphere is a little bit different because a sphere is a three-dimensional object. So the definition of a sphere is the set of all points in three-dimensional space equidistant from one point called the center. So this object is a sphere because it's equidistant from one point here called the center. And it's equidistant, these points are equidistant in three-dimensional space. Now, in order to do any sort of analytical work with a sphere, the primary element that we're going to need is the radius of the sphere. And the radius of a sphere is simply the length of the segment from the center to any point on the sphere. So that's a definition of the radius. And we're going to need this to do any sort of calculation. Now, the two primary calculations or ideas that I want to talk about in this part of the video is surface area and volume of a sphere. Let's start out with surface area. The shortened version of this is that if you were to take a circle that has the same radius as your sphere and cut it out and cut it into small pieces and fold them over the surface of the sphere, what you would find is you would cover exactly 25% of the sphere. Now, you know that the area of a circle is pi r squared. So, if one circle covers 1/4 of the sphere, then 4 circles would cover the entire sphere. So, we'd have 4 times pi r squared, which is the formula for surface area of a sphere. Now, that's a very crude way of introducing the formula for surface area of a sphere. If you would like to look at a more formal way to derive the formula for surface area of a sphere, check out my companion video on that goes through the process of using 3 two-dimensional shapes to approximate the surface area of a sphere, and it gives you a much better idea of where this comes from. So, surface area of a sphere is 4 pi r squared. Now let's take a look at volume of a sphere. Now the volume is the space inside the sphere, whereas surface area was just the area of the outer surface of the sphere. The volume encompasses all the points within the sphere. One way to think of the volume of a sphere is to consider a whole bunch of pyramidal-shaped chunks taken out of the sphere. If I were to transform this sphere into a bunch of pyramids, then we could approximate the internal volume of this sphere by the volumes of these pyramids. And that forms the basis for the derivation, or for a derivation, of the volume of a sphere. Now, if you're interested in that derivation, check out the companion video that I have that goes through that math and that process. So the bottom line here is that the volume of a sphere is 4/3 pi r cubed. And it's based on this idea of pyramidal-shaped chunks. And if you remember, the volume of a pyramid was 1/3 area of the base times height. And so that'll give you an idea of how this comes about. So we now have 2 formulas that we're going to use. Surface area, 4 pi r squared, and volume, 4/3 pi r cubed. And we're going to go ahead and use those in a couple of examples. These are very simple formulas, and it's a relatively straightforward process to use them in application. So let's go ahead and look at an example. Here we have a sphere, and we are given a radius of 5, and we're asked to find the surface area and volume of the sphere. My recommendation is generally to write down your formula first and work off of the formula. So let's first start with surface area, and I'm going to abbreviate surface area as SA, equals, remember it's 4 pi r squared. And we fill it in. That equals 4 pi 5 squared, which is approximately 314.16. Now let's switch over to volume, and volume is 4/3 pi r cubed, which gives us 4/3 pi 5 cubed, which is approximately 523.6. Fairly simple examples, very basic formula, but it's always good to include your formulas and work off your formula. Your problems aren't always going to be this straightforward, but let's go ahead and take a look at a composite solid that utilizes the volume and surface area of a sphere. In this example, we have a composite solid that appears to be made up of a cylinder forming its center portion and a hemisphere on one side and a hemisphere on the other. So let's analyze the surface area of this first. If this is truly a hemisphere and this is a hemisphere, if we add these two together, that gives us surface area of a sphere. So we're going to have the surface area of a sphere plus the surface area of this, actually the lateral area of this cylinder. Now we wouldn't use surface area of a cylinder simply because we're not including the bases in the calculation. So let's go ahead and start writing down our formula for our surface area here. So let's say that surface area is equal to the surface area of the sphere, so it's going to be 4 pi r squared plus the lateral area of the cylinder, which is going to be circumference times height. And as you remember, the net of a cylinder is a rectangle, and the length of the rectangle is the circumference of the cylinder. So let's go ahead and start putting in some values. We have, if you look over here, this distance is 8. That means that the radius of the sphere is going to be half that value. We'll just assume that that's a diameter of the sphere. So our radius is 4. So we'll just put down a radius of 4 here. That gives us a surface area of 4 pi 4 squared plus, now circumference is 2 pi r, so that's going to be 2 times pi times the radius, which is 4, times the height. And you can clearly see here the height of this cylinder is 17. Just as a side note, I've said this before, but I would like to stress, I would not do this as two separate calculations, only because it's too easy to drop a decimal point or to misread a value or something of that nature. Modern calculators have the capability now of entering chain calculations like that, so that's what I would recommend, that you would enter a chain calculation. And so if you're fortunate enough to have a nice little calculator like this, or one of the lower models that has the same or similar entry program, I would suggest using it because it reduces the amount of risk from mistyping a value. Plus 2 pi 4 times 17. And we get 628.3 as our approximated result. and that's surface area. Now let's take a look at volume. With volume, we have a similar situation. We have the volume of a sphere and the full volume of a cylinder. So we can just add those two volumes together. So we have volume equals 4/3 pi r cubed, which is the volume of the sphere, plus area of the base times height is the volume of our cylinder, area of the base times height, and let's just go ahead and put these values in. Area of the base is a circle, so that's pi 4 squared. Height again is 17. And then we would get a new value here. So we would have 4/3 pi 4 cubed plus pi r squared times 17. And that gives us 1122.6 approximately. 1122.6. And that is surface area and volume of spheres. Now the next topic we're going to look at is a comparison between Euclidean and spherical geometry. So I'm going to go ahead and wrap up this video here, and we will begin the next video with a discussion of a comparison between Euclidean and spherical geometry. So I will talk to you in the next video.